I'm going to try recording a video this way with the document camera, and we'll see. I'll ask you guys later, and we'll see if you like this better or the version with me standing at the board doing stuff. Anyway, so we're going to talk about resistance in Ohm's law. In an ideal wire, in an ideal conductor, electrons are entirely free to flow. However, in reality, there is some resistance to the flow of charge, and that is what this physical quantity of resistance is referring to. Ohm's law states that for a given resistance and current, the potential difference across the resistor is given by this. V equals IR. V is the potential, just like it has been for a while, potential difference. I is the current, and R, as you might expect, is what's called the resistance. Now, Ohm's law isn't a law on the same level that you would call, say, the law of gravitation, where Newton's law of gravitation applies to any two objects. Ohm's law applies to materials that are called ohmic, and many materials are ohmic, including a lot of the conductors that are typically used in circuits and electronics, but not all materials follow Ohm's law. Anyway, the most basic circuit that we're going to deal with can be drawn like this. So you'll have a battery, which is two horizontal lines, one of which is longer than the other, and there might be that symbol epsilon next to it, and that refers to, of course, the voltage of the battery. And then a wire is just like a straight line that you draw, and then a resistor, if you have a resistor, that's this sort of zigzaggy sort of line. So this is a very simple circuit. You've got a battery, and then you've got a resistor here. So that's just how you would draw that. And in this diagram, these wires are considered to be ideal conductors. So electrons are free to flow through them. Now, in reality, they have some resistance, but you can take care of that just by putting a resistor in the diagram that has the same resistance as that wire. Right? Resistance is dependent on a few things, and it kind of makes sense that it would be dependent on how long the wire is. It's dependent on how long the wire is. It's dependent on the cross-sectional area. And it's dependent on the material. Okay. Now it makes sense. The longer a wire it is, the harder it would be for current to travel down it. That makes sense. And the greater the cross-sectional area, the easier it is for current to travel down it, because there are just more electrons sitting around to be ready to flow. And then, depends on the material. There's a table of resistivities. So this property of the material has a property, again, it's rho. There are a lot of things that are rho. I don't know why. A given material has a resistivity, and that is the property that allows it to conduct or not conduct. And there's a table in your book on page 729 that has a bunch of resistivities. The division between conductors and insulators is because of a vast difference in resistivities. For example, rubber has a resistivity that is 10 to the 11th times greater than most conductors, which is why they would be classified as conductors, while rubber is classified as an insulator. So the distinction, while conductor-insulator is not a binary distinction, it's more of a continuum. There is a very big difference between these two materials. So we can quantify this relationship. The resistance of a given wire is equal to the resistivity of the material times the length of the wire over the cross-sectional area. And that encompasses all those relationships that I was talking about. So for example, let's say we have a time to go into the next class apparently. Say we have a wire that is 3.5 meters long with a cross-sectional area of, I don't know, 1.3 millimeters squared, and length, oh, I already said length, I'm sorry, that is made of copper. And there is a potential difference of 9 volts between the two ends of the wire. And I want you to find the current through the wire. It's a simple matter of applying the formulas. We know Ohm's law says that our potential difference is equal to IR, and now we know that R is equal to rho times length over A, and so our voltage is 9 volts, our current we don't know. The resistivity of copper, pulling out of that table, is 1.72 times 10 to the minus 8th, and I said the length of the wire is 3.5, the cross-sectional area is 1.3 millimeters squared, so that's 10 to the minus 3rd squared to convert it into meters, and from there we can calculate what our current is. And if we punch those numbers in, we get a current of 194.35, etc. amps. So those probably aren't very realistic numbers because that's kind of a ridiculously high current. But you get the principle. All right. Now, wires tend to get hot, and that's how a light bulb filament works. You know, the filament in the light bulb heats up, and because it heats up, it starts to radiate light and heat. And that's how oven coils work. There's a current running through them, and so they start generating heat. You've probably noticed that on your laptop, when it's been plugged in for a while, this little, box thing gets hot, and that's because there's a current running through there. So, wires do tend to get hot because the electrons colliding inside the wire start to move, and we know from kinetic theory that when things start moving around, that molecular motion causes a temperature increase. Generally, as temperature goes up, resistivity also goes up, which is why you try to keep things cool. There are fans in your computer and stuff like that. But when the molecules are moving around more, it's more likely for the electrons that are trying to flow to collide with stuff and slow them down. So because an increase in resistivity happens when temperature increases, there are some thermometers. There are some thermometers that use resistivity as a way to measure temperature. However, there are certain substances called semiconductors that work the opposite way. As temperature goes up, their resistivity decreases, which has caused them to be used in thermometers as well. Now there is a particular class of materials that are very useful called superconductors, which you've probably heard of. When they are cooled below some critical temperature, their resistance, the resistivity, drops to 0. And I don't mean like it's basically 0, like it actually is 0. Now this was first discovered as a property of certain materials, with critical temperatures of only a couple kelvins. And many, most superconductors operate at that temperature. However, they've been doing research lately, and so there is one substance, I forget which it was, but there is one superconductor that is a critical temperature of 125 Kelvin. Now that's still pretty cold, but if they, that's higher than it used to be, and if they continue to progress in superconductor research, and we get superconductors that can operate at room temperature, that would be, very, very useful, because they could do things like send, current down power lines with basically no loss, among other things. So that's an area of research that's ongoing. I think it's kind of interesting.